Mr. Sutton with one last lesson on conic sections. In this one, we'll be figuring out how to solve systems of second-degree equations. And systems of second-degree equations are used in many navigational systems, as we will see. For the warm-up, go ahead and solve this system of first-degree equations. Alright, so first step on this one, a lot of ways to do this. Probably the fastest would just be to add the two equations together. That would cancel out the y's. So we would have 3x equals negative 3. And then that'll be negative 1 for x. Don't forget to plug that back in to find the y value, though. Let's plug it into this second equation here. So for x equals negative 1, we can write negative 1 minus y equals negative 2. So adding the 1 over here, that's negative y equals negative 1. So positive y equals positive 1. And as a final answer, we have the point negative 1, comma 1. Before we explore the wonderful world of solving second-degree equations, let's figure out what our motivation for this is. Here are some real-life uses for this stuff. So first use, a lot of planes and ships use a system called Long-Range Navigation, or LORN for short, to find their location. The system sends signals to different radio towers and measures the difference in how long it takes the signals to get back. The difference can be expressed as a hyperbola. So the ship can be found where two hyperbolas intersect. Here's a visual. So here's a plane, and here's some hyperbolas. That's a little piece of a hyperbola. It's kind of hard to see, so here's another picture. In this next one, we have a ship sending out some signals, and here are these two hyperbolas that we see intersecting. For another application, GPS location works by seeing where 3 or more circles intersect. Here's you bouncing some signals off of cell towers, and there you are. So here is a second-degree system of equations. Looks significantly more intimidating than the first-degree system, but take a look at what we actually have for the different terms here. We could eliminate a lot of these if we just subtracted right off the bat. If we do that, these x squareds are going away, as are the y squareds, and the 6x's. So we just have the y terms and the constants left over. Negative 4y minus negative 22, that's plus 22, so 18y. And then negative 6 minus 12 will be negative 18. So we end up with 1 for y. Now we have to go and plug that back in. And it doesn't really matter which equation we use. So let's go ahead and do the first one here. So plugging in 1 for y, we got negative x squared plus 1 squared plus 6x minus 4 times 1 minus 6 equals 0. Collecting all the terms here, that's negative x squared plus 6x, and then we've got 1 minus 4 minus 6, so negative 9. Make our lives easier. Let's multiply everything by negative 1. So that'll be positive x squared minus 6x plus 9. We've got two perfect squares. This should factor into x minus 3 quantity squared. And just to double check, if we multiply x and negative 3 and double it, that does give us negative 6. So that means x is going to be 3. So our only point on this one is going to be 3, comma 1. Here's another system of equations. See if you can solve this one on your own. All right, what was your first step? Well, I know what my first step would be. I always look to see if I can subtract these and get rid of some things. If we do that, the y squareds are going to go away along with these 12y's. That'll leave only terms with x. There are going to be some second-degree terms in there, but that's okay as long as we only have one variable. So subtracting then, that's going to be negative 3x squared minus 15x, and then this will be positive 42 if you add 43 there. And we can make our lives a little bit easier if we divide everything here by negative 3. So that's x squared plus 5x. And then, let's see here, that's going to be minus 14. Two things that multiply to negative 14 and add up to 5. That would be negative 2, positive 7. So we can say x equals 2 or negative 7. But we're not done. We have to actually now plug each of these x values back in to find some y values that go with them. So plugging in 2, and for this one, I'm going to use the first equation here. It looks a little bit less intimidating, smaller numbers. So that'll be 2 times 2 squared, which is going to be 8. We've got 10 times 2, that's 20. So we have y squared plus 12y, and then 8 plus 20 minus 1. That's going to be 27. Things that multiply to 27 and add up to 12, that would be 3 and 9. So we have y equals -3 and -9. So that's going to give us 2 answers so far. And I'm just going to write them down now so we don't forget about them. We're going to have 2, -3 and 2, -9. We're not done, though. Now we have to plug in -7. I'll use the same equation. So if x equals -7, then we've got 2 times 49, which is 98, and this is -70, so that's a total of 28, minus 1 is 27, and we have, oh wait, it's the exact same equation. So the factoring is going to be the same, the y values are going to be the same, so we're then going to end up with 2 more answers, -7, -3, and -7, -9. So 4 answers for this one. All right, let's wrap things up here. So for the wrap-up, what is the maximum number of times 2 different conic sections can intersect? And why? Think you got it? So it turns out it can be up to 4 times. We could show this graphically. If you think about a hyperbola inside a circle, kind of like a baseball sort of shape, or think about it this way. With x squared and y squared, each coordinate can have at most 2 different values. Remember solving quadratics for each of them on that last example? So there's really only 4 xy combinations that you can possibly have. So this concludes our lesson on conic sections, systems, and also the chapter on conic sections. Until next time, this is Mr. Sutton signing off.